Hi. Um, in this lecture, we will cover a topic that we left over to a later point, namely the function pointers to functions. Now, a little bit theoretical background about it. Normally, we have, of course, the way to define functions. But what about having a function that takes another function as an argument? Don't confuse this with something like tangent arc sine x plus something 0.1 stuff. This is not, or even if I don't have this, this is not a function that takes as an argument another function. This is functional composition. You know this. Those that come from the Turkish system, you will know this as fogs and gauffs. Remember? Functional composition. That is not what we are talking about today. What about having a way to define a function f, which takes some function f in some many other arguments, x and y and z, nothing specific about that, and at call time you send from here down a sine x, for example, or alternatively you send, sine down, or you send down square root function. Function without any argument yet. The argument presumably is going to be cooked up in this f. So, for example, f could have been something where you return 1 over square root of 1 plus f something for this. Take as an example. How could we do this? When it is called with the sine function, this shall return to me sine y plus z over square root sine squared x, and if it is called with the circulator function, then something totally different with this will happen, and this will be replaced with totally different, right? Such a function is called a higher order function. If it is admitting another function. It is a higher order function of first degree. If you have a function definition which admits another function of this type, for example, which admits another one, then you have a higher order function of the second degree. This is something new to you. I know this was not presented to you in your math courses in your high school mathematics, but it exists. Mathematicians play around with these. Not all languages provide this, but and it's also some sort of an advanced topic in programming, but C does. By the way, Python did it as well, but we never mentioned about it because it was an introductory course. Now, how we do this? How we do this? Let's assume first the simple case. Let's write exactly the same stuff over here, an f function which takes here a function, we will come to the definition later on, and let's say 2 or 3 additional arguments. Let's have 2 arguments, x and y. First, define them. Floating. Float x and float y. And here I want to say I will send from here a function. How I will send it will become clear in a second, but first, what type of a function? What does this function return as value? For example, I want to send down sine x or square root of x. I know very well that both of these functions return floating points. So that's what the function returns. And then comes what it takes as an argument. What does it take as an argument? It takes another float as an argument. So it's something that takes a float as an argument. You can also put here a dummy argument, but it will not enter in any mathematics, nothing, just it will be that dummy, so you don't have to put it there. Now, something must stand for the variable function entity, right? And how we do this is something similar to the array, pointers to the arrays. Remember that stuff? You put the entity into parentheses. Here we will send down the function by a pointer to the function. I will just explain what that function, what that pointer is, but therefore we put here a function and a dummy name for it, f for example. Okay, so that is the way you define it. A type, an argument list, list of types, and then in parentheses here goes in an ID. An ID that will play the role of a function pointer down in this definition. that is the trick. So the function returns tau, takes these as argument, in our case a single argument function, and throughout the definition I will call this function f. Okay. Now cook up something. Take these, multiply them, just as an example, x times y, and now send it to the function that is coming from the argument of f. You would expect it to be something like this, which is not true. Don't make this mistake. You have to, what comes down from f is a pointer, and always you have to dereference a pointer if you want to go to the object. So the object that is referred to, is pointed to, is a function, so you derefer it. Since this will have another meaning, you put also a parenthesis around here. Yes, this is the function. This is the function pointer, and this is the function. Practically, what is sent down in the address part of the pointer to the function, is the entry point address of the function. Entry point address of the function. The entry point of a function is the point which is called the moment the activation record is created and we jump to the function. Remember that activation record lecture. Somewhere we created the activation record, the calling point created the activation record, okay? Then made a subtle jump to a position in the memory where the function was defined in terms of a machine code. That point is called the entry point of that function. So in the address part sits the entry point, and here sits an information about this one. Return value and argument types, right? A complex information sits there in a function pointer. This is important to create a proper activation record that will properly be received by the called function. So you shall not make a mistake. Okay. This is just an example. So I divide this entity by something like 1 minus or 1 plus I slightly change it from the previous example, right? So it is something like f x multiplied x dot y over square root 1 plus f of x f of y. Don't try to make any sense out of this. This is just an example for just a function. Right? Okay? And now return. Return. Yes. This is a function call with some arguments, actually single argument. The compiler will go and fetch from the definition of the local variable f, which is a pointer to a function, will go and fetch that this return takes a floating point in and returns a floating point also, creates an activation record for a single argument and a return value box that is a floating point, and fill it in with the result of x multiplied with y. This is the definition of f. Wherever I call f, I will call it with a function which has exactly this defined pattern. Sine, for example. It doesn't have to be a built-in function. There is no concept of a built-in function. Built-in functions are just functions defined by a person sitting somewhere in a lab, right? It can be your function, it can be some built-in function coming from a library, but it has to strictly obey this rule. It shall take a floating point in, and it shall return a floating point. Why? Because we have defined it this way. Could it be something else? Definitely yes. Everything is possible. Here you can define any sort of a function. There is no restriction on this. Absolutely no restriction. Any function can be sent down as argument to a function. Does it have to be the first one? No. Can I have more than one functions going down into a function? Yes. So, something like this is a possible call. Another possible call is something like this, right? For this call, SQRT will be substituted in place of this. So x will be square rooted and y will be square rooted and get multiplied. In the other case, the sign values of x will get and y will get multiplied. For a moment, you may think, why shall I use something like this? Why shall I use it at all? Think of a case where you are supposed to write a sorting algorithm. A sorting algorithm. What will it take in? It will take in presumably an array or a pointer to the first element of an array. So here you have something element pointers an array, comma, integer, length of the array, okay, right? And then you write down your sort algorithm. There are various sort algorithms. You will be seeing all of them in your algorithms course. Bubble sort, merge sort, quick sort, heap sort. You will analyze their complexity, memory complexity, more important than that, the time complexity. I can write down here one example, but it's not important what the algorithm is. Somewhere at a single point or at several points of the algorithm, it will be the case that an array element I compare to array element something else, J, right? So all sorting algorithms need this. It is the way you sort. Is it an ascending order sorting or a descending order? Which one comes first? The biggest one? Even the definition of being biggest is something fishy, something flexible. For example, will I compare the ASCII codes of the letter, if it's a string sorting, for example, or will it be case indifferent? So, what about Anne, Ali, Baba? Where will Ali live? If it is case dependent, and if you obey the ASCII order, then Ali must go down over here. So it's Anne, Baba, Ali, because Ali, the A here is a lowercase, and lowercase letters come after the uppercase letters. But you know very well that in a dictionary, for example, this doesn't make any difference. So, Ali would appear actually here if it would be case independent. Which way? Also, where will go the Turkish characters if they exist in the string? Share and check. This boils down to specific points in the algorithm where you have an array element, an arbitrary array element, compared to another arbitrary array element. But what will this be? This one? This one? Or some special function? So actually, the correct way to do is to put this into a function that you would call something like compare. Compare Arij with this, right? It's much better to call it with compare. But where will compare come from? In this case, it is very convenient to have a higher order function definition for sort. So it will be sent to sort as a function point. Compare. Compare will make a logical decision in this case. So it's either 0 or 1, so it's an integer. It returns an integer. And what does it take in? Oh, that depends on what the array elements are, but they are something. So they are element type, right? So it is an element. And the second one, that is also an element. And now, in my sort, I use very nicely compare the local argument which is bound to a function pointer, ID reference, it becomes a function, and I use it with two elements, two arguments which are compatible with this, whatever element is. That is not my concern right now. Okay, and you can use it as much as you like in the argument. How will I send that several alternative functions? I will write assembling compare. Let me take it shorter. It will return an integer. It will take an element x element y in and return x greater than y. Then another alternative in descending compare element x element y of course, in this case, I need something which defines greater and lesser for the element. Sorry for that. So I will make it like this. For being greater than and return compare x versus y for being lesser and so on, right? and maybe some third type, as we gave the example for the ASCII characters. I cannot go further into the example because we have to specify what the element is. The element maybe is a structure. Structures cannot be compared with the lesser sign or equal sign. Then presumably I will go down in the structure to a subfield and compare two subfields. But the idea is, for this one, however I represent it, if x is said to be greater than y, I return 1, and here I return 0, that means the other way around. And when it's time to call sort, I will call it with a array or a pointer to a malloc entity, let's say 105, and then here in will go either this one or this one. Or decom. Note that nothing comes after the function. So what we have learned is the function name defined is the pointer to the entry point of the function in C. Okay, this completes the function pointer topic, and we have a break.